Hey guys, so this is section 6.8, calculating equilibrium partial pressures and a mixture of ideal gases. This is basically just an example of how you do it. We'll pick, just like the book did, a really simple example, dissociation of molecular chlorine gas into atomic chlorine gas. So the idea is you have some chlorine gas in a container whose temperature you can adjust, get it pretty high so that you get partial dissociation into the atomic chlorine and you have this equilibrium going on. So if you maybe you remember ice tables from Gen Chem. It's an equilibrium thing, initial, change, and at equilibrium. So if we call the amount of chlorine that we start with N0, we don't have any atomic chlorine to start with, and then at equilibrium, we'll have lost X. We'll call this X, moles of chlorine. X stands for moles of chlorine lost, which means we make 2X moles of atomic chlorine. And so at equilibrium, we'll have N0 minus X moles of chlorine and 2X moles of atomic chlorine. And we'll use this in a minute, but we're going to define the degree of dissociation, beta, as X over the amount of chlorine that we started with. It's just what fraction of this molecule dissociated. So definition of partial pressure is the mole fraction of that gas times the total pressure in the container. So the partial pressure of chlorine would be the mole fraction of chlorine times the total pressure. Once more, guys, watch out for these X's. This is a chi, stands for mole fraction. The X's stand for moles, how much is lost or gained. So likewise, the partial pressure of the atomic chlorine in that container will be the mole fraction of atomic chlorine times the total pressure. Also, the definition of mole fraction is the moles of that species divided by the total moles in the container. So for chlorine, the mole fraction would be the moles of chlorine divided by the moles of chlorine plus the moles of atomic chlorine, which from our ice table we see is N0 minus X for moles of chlorine, and then N0 minus X plus 2X, which works out to be just N0 plus X for the total moles. Likewise, the mole fraction of atomic chlorine will be the moles of chlorine, which is 2X, over the same thing, which is N0 plus X. So what we're going to do is substitute these expressions here in for the mole fractions in these equations right here, and we see that the partial pressure of chlorine is this times the total pressure. This is supposed to be atomic chlorine. I'm so used to writing Cl2. Partial pressure of atomic chlorine is 2X over N0 plus X times the total pressure. All right, so carry that over. And so now we know that Kp, it's equal to the partial pressure of chlorine over 1 bar squared divided by the partial pressure of chlorine over 1 bar. So the products of reactants raised to the powers of the coefficients, basically. And all we do is we substitute in here our expressions up here. So for the partial pressure of, again, that's supposed to be atomic chlorine, 2X over N0 plus X times total pressure over the 1 bar, square that whole thing, and on the bottom, partial pressure of chlorine up here, times the total pressure over 1 bar. When you multiply this out, so we get 2x squared is 4x squared. One of these N0 plus x's cancels with this one. We have one N0 plus x left in the denominator. We have N0 minus x in the denominator for this. One of the total pressures cancels. We have one left in the top. Likewise, one of the 1 bars, the standard pressure, cancels and we get 1 in the bottom. So we get this expression here. If we multiply out the two terms, it ends up get plus N0x minus N0x, they cancel, get N0 squared minus x squared. So that's what we got. Remember, beta, the degree of dissociation is X over N0. So we're going to write this, well, our goal is to write the Kp in terms of beta. So if I take this part of Kp right here, 4x squared over N0 squared minus x squared, and multiply it by 1, which I can always do in the form of 1 over n0 squared over 1 over n0 squared, because that's just 1, right? What we get is 4 over x squared over n0 squared, which is beta squared. N0 squared over n0 squared is 1. X squared over n0 squared is beta squared. So that means that Kp, substituting this expression in here for this, we get 4 beta squared over 1 minus beta squared times total pressure over the standard pressure. You can do this. Okay, so notice this is for this particular reaction. If it's a different reaction with different stoichiometry, it's going to have a different form. But this, you could do it for any gaseous reaction. Notice that we saw before that Kp, it's a function of temperature only, which means that beta must only be a function of temperature only too. We can also solve this for beta, the degree of dissociation. So if we take this, and it's just algebra, so we multiply through by 1 minus beta squared here, distribute the Kp inside, we get Kp minus Kp times beta squared, bring add Kp beta squared to both sides, we pull beta squared out in front, we get 4 total pressure over standard pressure plus Kp, all times beta squared equals Kp. That means that dividing through by this stuff in parentheses, bring this down there, right? Taking the square root, now we have an expression for beta in terms of Kp.